Okay, so I want to continue with the first section on Calculus 1, which is functions. Right, so where did I get up to? Problem 17, which was finding the roots of functions, And now it's time for me to look at these functions here and determine their domain and range. Determine the domains and ranges of these functions here, respectively. All right, so just want to maximize the amount of room that I have for my notes. And let's get started. So I believe that the domain of function y here is the entire set of real numbers. As for the range, well, that's a more complicated question, isn't it? So it's a positive quadratic function, and therefore it's a classic U shape or parabola, which opens upwards. And therefore it will have some negative number as the lower bound, as the greatest lower bound of its range, and then it will be all the numbers above that. All right, but how can we find the minimum of function y? What you do is you find the line of symmetry, which is found by negative b over 2a. So in this case, it would be 2 over 6, which is a third. 2 over 6, which is a third, so x equals a third. And then you find out what y of 1/3 is, and that will get you the global minimum. So a third squared is a ninth, and 3 over 9 is a third. And then we must take away 2/3, and then we must add 1. A third take 2/3 add 1 is 2/3. So the range of y will be, yes, it'll be 2/3 to infinity, like that. I believe that's right, but we'll have to check. Yes, we agree about that, the domain. I choose to write the symbol for the real numbers. And we agree upon the range. We agree about that. That's great. Problem 19 is another quadratic. And therefore the domain of G is the entire real number line. And this is a parabola that's opening up, that's opening downwards. So it's an upside down U shape. And we perform the same procedure as before. First, determine the line of symmetry using negative b over 2a. So that would be 4 over negative 2, which is negative 2. And then make the substitution of negative 2 into G to determine the y coordinate of the global maximum. So the negative of negative 2 squared is negative 4, and then negative 4 plus 8 is 4, and then 4 plus 7 is 11. So it should be 11. the range of G should be negative infinity to 11 inclusive. While we're here, we'll try problem 20. So here we have a function 2 plus the square root of z squared add 1. Now, for the domain, you may see the square root symbol and think that I have to be cautious here, as you're not allowed to take the square root of a negative, at least in this context. However, notice that z is squared, and therefore that ensures that this will always be positive, a positive quantity, and furthermore we're adding 1 to it. So it's all good. So the domain of f is the entire real number line as well. As for the range, we'll want to minimize the number underneath the square root sign, the z squared add 1. And to do that, I believe that it's kind of obvious that you'd have to input z equals 0, as anything non-zero would constitute a positive quantity. So let z equal 0, and when we do that, we have 2 plus the square root of 1, which is 3. So the range of f is 3 and above. And now we check. Yeah, that's correct. The range is correct and the domain is correct. That's good. And now we check. Okay, the domain is fine and the range is fine. That's great. Problem 21. What is the domain of this function? Well, we want to ensure that we don't have a negative number underneath the square root sign. So this 3y here, we don't want it to be anything less than negative 14, anything less than negative 14. And therefore we don't want y to be anything less than negative 14 over 3. All right, so the domain of h will be anything greater than or equal to negative 14 over 3. As for the range of h, well, okay, so we'll want to minimize this. We'll want to minimize 14 out of 3y. And therefore we need to focus on minimizing this 3y. And I think the as stated, I mean, you just input negative 14 over 3. So that should be 0, and that should go to 0. And I think it's 0. I think it's 0 and below. 0 and below. Yeah. There's no way to get a positive quantity out of this. Okay, and now we'll consider problem 22. So we have m of x, which is 5 minus the absolute of x at 8. So what is the domain of this? Well, that would be the entire real number line. As for the range of output values, this will be an upside down V shape, as the absolute value function only outputs a non-negative quantity. So we'll want to make this 0. So this will be, so m will only output 5 and below. believe. And now we have to check. All right, so that's all good for the domain, and that's all good for the range. And similar remarks here. Now, I don't understand why he... Oh, right, okay. Because I guess finding the range of these functions is more difficult somehow. That's totally fine. But nonetheless, there are quite a few questions here. In fact, there's 10. 10 it seems. So, let's get started. So the domain of f. The domain of f. We need to focus on the denominator. We're not allowed to have zeros in 0 for the denominator. So 12w takes 7 equals 0. Solving for w, we have w equals 7 over 12. So w is specifically not allowed to be 7 over 12. So how would I signify that? Perhaps like this. And the 24th function, here we want this to not be 0, the denominator, which is a cubic, to not be 0. And so we have to find its zeros. We have to find its zeros. So factoring out z, we have then z squared at 10, z at 9. And that is z at 9 times z at 1. So the zeros are 0, negative 9, and negative 1. And thus, for the domain of function r, I would say that it's the reals, specifically excluding 0, negative 9, and negative 1. And problem 25. Right, these are always kind of a pain to factorize. Wait, let me just do the discriminant upon this. So b squared minus 4ac, so that'll be 1 plus 16 times 7. Or 1 plus 16 times 7. 16 times 7 is, I'm not sure why I'm faltering on this, 112. And so, yeah, so it's not factorable. Darn it. So no matter. Just equate it to 0 and then complete the square. Or use the quadratic formula, whichever you like. So personally, I want to do it this way. Well, hold on. Let's just say an eighth. And then we have to take away 1 over 64. So add 1 over 64 to 7. And then t is this right here. Seems a little bit large for that, but 448, 449, that's fine. So specifically, T is not allowed to be this. So the domain of G is the real, specifically excluding -1/8 minus that large square root. Let's actually do the courtesy of cleaning up that square root, yeah? So 7 times 64 is 448, so 449 on top and 64 on the bottom. Now 449, not 3, not 7, obviously. 11, no. 13, no. 17, no. I think it's 449 a prime. Yes, it is. Okay, so that's nice. So yeah, root 449/8. It appears so anyway. I don't know if that's true right now. -1/8 plus root 449/8. But we better check these. Right, so we've checked all those. So that's fine. 23, 24, 25. Good. We agree. Yes, that's what I just did. We agree. That's fine. And all right, man. Okay, I've got to learn how to take control of this. Oh dear, look at that. I didn't divide that by 4. What a blunder. Gotta fix it. All right, let's see where it ends up. Oh no, it's on the screen. Uh-oh. Right, as long as I'm not looking, I can still salvage the opportunity to fix things. Right, okay, so that would be 7/4 now. And then we have to take away a 64th, and so it's 7/64 plus a 64th. And what is 7 times 16? 112, and so it becomes 113/64, which I know to be a prime. And so yes. All right, we fixed it. Brilliant. Okay, continuing. Problem 26. We have to find the domain of this function. That would be anything. Oh. The domain of this is every real number from -5 to 5 inclusive. I believe. And here for 27. Okay. All right, so that's trickier. We want that to be positive, and how to figure that out. Well, we've got to do a little bit more analysis of this then. So x squared, take x, take 20. And does that factor? I hope so. Yes, it does. Okay, brilliant. Okay, that's great. So now I can visualize this quartic, this fourth degree polynomial. I can visualize it as having a root at the origin and at 5 and at -4 somehow. And because it's a quartic, positive quartic, it will go from top left to top right in the U shape somehow. It'll trace through these. So let's think how it will actually do that. How that's actually possible. I think it will do that. The W. I think it will do the W shape. And therefore, what do I exclude from this? All right, so I believe that the domain of H is -infinity all the way up to -4. I should really mark these on. All the way up to -4. And do you include -4? Yes. Then also stick in the original, the single point 0. And then 5 and higher. I think so. Now for problem 28, again, we focus only on the denominator. And we want to make sure that that's not 0 and not negative. Not 0 and not negative. Strictly positive, as they say. So how to do that? First, let's figure out where it's 0. Factor out t, so we have t squared minus t minus 8. And that's not factorable, is it? Darn it. Darn it. All right. Okay. Well, we have t equals 0. That's one root. Now we have to take care of this. So just set it equal to 0. And complete that square. You do that, and then you have to take away a quarter, and so you have to add a quarter on to the right. So 8 1/4 means 65/4. So t is half plus or minus root 65/4, like that. And there's your other root. Now what? Now we have to figure out where it's negative. where it's negative. So we have to interpret the zeros of the cubic. So we're going to do that graphically. So it passes through a half plus the square root of 65 over 4, which is somewhere over here. I don't know where. The square root of 65 over 4. Well, that's about 16-ish. So it's about 4-ish. So it's somewhere like there. Okay, fine. There are the roots. All right. And it will have this shape here, just like this. Now, what this means is here's how we're going to restrict t so that it's valid. I just want to highlight that that's where I'm considering the zeros of the cubic. And this is how I'm considering the negatives of the cubic by sketching it. It's not terribly rigorous, but it's fine. Thus, the domain of P is from a half minus root 65 over 2 all the way up to 0, but not including that, coupled with a half plus root 65 over 2 all the way to the end of the rainbow. Positive infinity. That's what I think. So there's the next 3 done. Now let's see if it's right and how right it is. Okay, good. So the domain was done correctly. And here, that's great. Okay, we got that right. And here, oh, darn it again. Keep messing up with these coefficients, so it's just simply not completing the square right, I think. Plus a quarter. Look. I mean, it follows the same logic, right? But why the different solution? Because continuously mess up the arithmetic of completing the square, don't I? Right. Gotta get it right. 8 over there, minus a half of that. So minus a quarter of that. So plus a quarter into 8. Eight and a quarter is 33 over 4. Goodness me. Not really awake, am I? Right, okay. There should be multiple ways in which I should be catching really silly blunders like this. But it's all fixed now. And the point is, I got the process, the thinking process right. So that's good. All right. Now for the next four. Problem 29. Okay, so we need to make sure that this does not be negative. So for this one, z has to be greater than 1. 1 or greater. And for this one, z has to be greater than -6, which is a stronger condition, this. So we'll just say that much. Now for here, all right, so 2y at 9 has to be greater than 0, greater than or equal to 0. So 2y has to be greater than or equal to -9, so y has to be greater than or equal to -9/2. For the first third, and then for the next one. The denominator, in the denominator, we see that y has to be less than 2. Y has to be less than 2. And it may not be 2 itself. Yeah, so y has to be less than 2. So the domain of H is that. Problem 31. Let's see. X may not be 9. And here, x squared minus 36 has to be greater than 0. So x squared has to be, x squared minus 36 has to be greater than or equal to 0. And so x squared has to be greater than or equal to 36. And so x has to be greater than 6. Oh, right. Okay. Yeah, I get it. That. Okay, and now for 32. All right, so the first side doesn't restrict y in any way. But for the second one, we've got the cube root of 1 take y. And I think that's fine. That doesn't restrict it in any way either. So I think the domain of Q is the reals, I think. Right, well, we better check these for. Great, that's correct. That's correct as well. Less than or equal to 6 and greater than or equal to 6. Yeah, I mean, I'll allow it because that is like what I'm saying, obviously. And for this one, yes, I think it's the reals as well. Yeah, okay, so that's all good. All good. Time now to do the last 4 problems. For these, compute f composed with g and g composed with f for each pair of functions. Okay. For this, we pick up g and feed it into f. So as for here, pick up f and you feed it into g. Seven times that is, well, it's 28x minus 7. So it's 28x minus 1. Pick up g, feed it into f. So it'll be 5x squared minus 70x plus 2. Pick up f, feed into g. So it'll be the square of 5x add 2, which is 25x squared. 25x squared add 20x add 4. And then take away 14 times that. So minus 70x minus 28. So in summary, g into f. So square 8 take 3x. All right, then we get 9x squared minus 48x plus 64. And then multiply it by a negative 2. So we're going to have 6x squared minus 16x. And then add 1. And compute. So we'll have 15x squared minus 64x plus 65, I believe. And now g of f of x. So we pick up f and put it into g. So we have to square that quadratic right there. So I'm going to make some room to do that down here. x to the 4 minus 4x cubed, 2x squared plus 4x squared, so 6x squared minus 4x, and then plus 1. That's what happens when you square it. Then we have to do 8 minus 3 times that. All right, so the final result, it'll only affect the constant at the end. So we just multiply that by -3. So 12x cubed, take 18x squared plus 12x. Then this will become -3, and then we plus 8, so plus 5. And I think that's fine. Now for problem 36. I'm going to do f of g of x. So we're going to pick up g and put it in f. So we square that out, and we just get what's underneath the square root sign. So x squared add 5 add 3, which is x squared add 8. And then g of f of x. So we pick up f and put it into g. So we have to square x squared add 3, which will be x to the 4 add 6x squared add 9. But then we have to add on 5. So it'll be x to the 4 add 6x squared add 14. Like that. And now we must check each solution. Okay, so the first was computed correctly, and so was the second, so that's good. That's correct as well. For problem 35, is it? All right, so strangely, this one was actually done, the second one was done accurately, but this one was not. How is that so? Oh, because of the indices. Right, we are to square 8 minus 3x squared, so that would be 9x to the 4, in fact. Then minus 48x squared, in fact. Plus 64. Then, is that all that's necessary to correct it, right? I think. Okay, so it should be 9x to the 4 minus 42x squared minus 16x plus 65, is it? Still not quite right. Nine x squared minus 9x to the 4 minus 48x squared plus 64. Okay, that part's right. And then negative 2 lots of that. So 6x squared would it be minus 16x? Minus 16, just minus 16. So in fact, there's no linear term. (64 minus 16 is 48 plus 1, so 49. And now it's correct. And last. All right, that's correct. And that's correct. And that's good. Okay, great. All right, so now I'll practice inverse functions. Can move on from that. Yeah, I want to try this. Inverse functions. No, I'm not computing the compositions as well. All right, so I'll just compute the inverse. That's quite fine. So for this simple linear function here, it would be x minus 15 over 6. Those are straightforward and can be done just in your mind. For this one, (3 minus x over 29). And for this one, cube root of x minus 6. And for the fourth one, take 21 divided by 4, take the fifth root, and add 3. So x minus 21 over 4. And add 3. Of 5. And then I'll check at this point to make sure I'm not going completely astray. X to the 5, take 9, and then divide by negative 11. So 9 take x to the 5 over 11. Great. Yeah, as stated, I'm not computing the composition. Just a waste of time. That's done. And that's valid. And that's correct. And that's correct too. And that's good. All right. Okay. X to the 7 take 8 over 5. Now, here's where it requires some thought. First, I'll set y equal to 1 add 9x over 4 take x. Then, I'll multiply both sides by 4 minus x. Multiply it out. And remember, my goal is to get x by itself, so I'll put the x terms on one side. I'll have 9x at xy on the right and 4y take 1 on the left. Factor out x to get 9 add y, like that. And finally divide through by 9 add y. And thus, the final answer should be 4x take 1 over 9 add x. Now for the 8th problem. Similar. So same strategy. Y equals 6 take 10x over 8x add 7. Times both sides by that. So 8xy add 7y equals 6 take 10x. Move everything over. Factor out x and divide through. And there you go. So 6, 7, and 8. We'll check these. Yep, that's correct. That's correct. And that's correct. Excellent. Okay, now practicing trig functions. Very nice. So I'll save this as inverse functions. And I get started with trig functions. Okay, not bad. Without using a calculator. What is the cosine of 5 pi over 6? Now, I just know this, but how am I going to convince someone else of that fact? Mm-hmm. I wonder how they convince them of this fact. Because what I think would be most convincing to most students is to just say what it is in degrees first, which is 150 degrees. And then to say to them, imagine the sinusoidal curve, the classic sinusoidal curve, and then you're 30 degrees before a trough. What is the value of that? So it's minus 3 over 2. Minus root 3 over 2, rather. So that's how I think of it, but what does he say? If he says something fancy like, did take off pi over 2 and all that stuff, is he going to say stuff like that? He is. All right. Well, sorry, but I just don't think that way because it's too slow. It's just too slow and impractical for me to think that way. Although I do understand it, I just don't think it's that practical. Sine of negative 4 pi over 3. So sine is an odd function. So straight away we'll do this. And then 4 pi over 3, pi is 180 degrees, and then you add on a third of it, and so 240, and so yeah, so it's 30 degrees before a trough again. So I believe it's also that. As there's only 11 here, I'll just do 5 and check them all. So tan of 3/4 of pi is tan of 135. So -1. Secant of negative 11 pi over 6. Well, secant is the reciprocal of cosine, and therefore, it's an odd function as well. It's an even function as well, and therefore it's symmetrical. And so we are going to compute 1 divided by cosine 11 pi over 6. So that's 330 degrees. And so 30 degrees before the peak, which is root 3 over 2. And then the reciprocal of that, so 2 over root 3. And then the fifth one. Oh no, wait, what? Oh man, I've missed out so many. How did this happen? Well, fortunately, I can just move stuff. Okay, so sine of 7 pi over 4. Well, that's pi and 3/4 of pi. So it's 45 before the full 360. So it'd be negative root 2 over 2. Then you had cosine of negative 2 pi over 3. Cosine is even, and therefore I can just compute cosine of 2 pi over 3, which is cosine of 120 degrees, which is 30 degrees below the axis, so a half. Negative a half, beg your pardon. Negative a half. I think that's right. Right. How on earth? First of all, you forgot to wait. I just simply forgot. Just stop paying attention to that minus sign right there. Obviously, it becomes a plus. Better make sure that the other one is right. I think so. That's correct. That's correct. That's correct. That's correct. Okay, problem 7. Cosine of 8 pi over 3. Reduce it, so subtract 2 pi from that. So it'll be the same as cosine of 2/3 of pi, which is cosine of 120 degrees, so just 30 degrees below the horizon, if you like. So it should be negative a half, I believe. Now, tan of negative pi over 3. Well, tan is an odd function, so straight away convert it to this. Now, to compute tan of pi over 3. Well, pi over 3 is 60 degrees, and tan of 60 degrees is something that should be known. It's root 3, so it should be negative root 3. Tan of 15 pi over 4. The period of tan is pi. The period of tan is pi, or 180 degrees. And so just keep on subtracting 4 from the numerator. Keep doing so until you get within the range of 0 to pi. So when I do so, it goes from 15 to 11 to 7 to 3. Three-fourths of pi. 3/4 of pi. Well, you should kind of be visualizing that. So it's in the second quadrant. It's in the second quadrant, and it's sort of like a 45-degree triangle over there. So -1. Anyway, I suppose I'm getting a little bit tired. Let's see, sine of -11 pi over 3. So that's the negative of sine of 11 pi over 3. The period of sine is 2 pi. And so here we would take away 6 from the numerator. No, wait. Right, so 6 pi over 3. So take away 6 from the numerator, yeah. So the negative of sine of 5 pi over 3. Five pi over 3. What's that? Pi and 2/3. Now, why is this occurring to me slowly? 30 above the trough. So the negative of √3 over 2, but then the negative of that. So that, I suppose. So let's do this. Let's check these before the final one. That's correct. That's correct. That's correct. And that's correct. Okay, good. Now the very last one. The secant of 29 pi over 4. The secant function is 1 over the cosine function. And like the cosine function, it has a period of 2 pi. 2 pi in this context is 8 pi over 4. So continuously subtract 8 pi over 4 until you get within the range of 0 to 8 pi over 4. Okay, so when I do that, I'll end up with 3 pi over 4. Now, what is the cosine of 3 pi over 4? Well, that's the same as the cosine of 135 degrees, which is negative √2 over 2, but then we have to take the reciprocal of that. So it'd be negative 2 over √2, which is negative √2. And let's check. All right, that's correct. I'm kind of curious what these assignment ones are. All right, they're all fine, but I'm not going to do those. Just going to save this. And see what's next. What appears to be next is solving trig equations. So I may take a small break before I try such a task. Be well, be well.